Hello everybody, this is Nino, and in today's video I shall be talking about swarm intelligence, and I shall present to you some of my ideas regarding that topic. So far we have been discussing logical triangulation, its simplification by reasoning through patterns and learning by means of challenge-reply pairs. I have shown you also my concept of fragmentation sets, which should allow for faster pattern comparison so that your systems learn more easily. But there is one further way of enhancing interaction with the system, and namely using parallelization. If you are looking at an artificially intelligent agent, here symbolized by an evaluation function, which is this little circle, operating on the system's knowledge base, which is this square, you may quickly hit a wall of what is practically computable by running into what is named the combinatorial explosion, and your system may exhibit an exponential increase in complexity and computing time as you want it to gain further capabilities. So a more capable agent might be theoretically well imaginable, but practically not computable. One possibility to evade this issue is if you are using several agents to reason on a problem at once. At least you will be able to combine their knowledge into a bigger knowledge. It may also be easier to scale, not only because the growth is not exponential, but even because you may use several computer processors in parallel in order to reason on your problem. Your disadvantage, obviously, is the lack of interconnection. It is this interconnection, however, which oftentimes causes this combinatorial explosion, and there are lots of problems where you say that this lack of interconnection of every possible aspect with each other possible aspect is not a big loss at all. Now, this set of artificially intelligent agents, I am saying they are forming a swarm. Each of them I shall refer to as an insect. I believe particularly apt for usage in a swarm intelligence are agents whose evaluation function is normally operating on multiple independent data, and where you can estimate the quality of the solution of each agent. So you present to the agent a problem and you're getting from it a reply, and you can say how good the reply was. And optionally, it would be kind of nice if you could make out some sort of cheaper function which is going to give you an idea about the quality of the solution. Some sort of pre-evaluation or estimation function. You know, like when you are estimating the square root of 9 and you don't know it's 3, you can still say that, well, it will be somewhat below its average of 4.5. That would be such a sort of pre-evaluation function where you don't get a precise result, but you get an idea of what your result might be like. That can help in the estimation of the solution. You can actually profit from parallelization even if each of your agents is single-threaded, because you can run, by using a swarm intelligence, several single-threaded agents in parallel. Now, what is the swarm, which I will be talking of here? I say, in my designs, the swarm is a set of multiple copies of the same type of agent, and each is operating on its own knowledge base. Each of those insects, as I call them, has an evaluation function for a problem and its own autonomous knowledge base whereupon this function is operating, and the set of these insects is constituting the swarm. So what does it look like when the swarm is reasoning on some sort of problem by means of challenge-reply pairs. Well, you're having here some pattern which is delivered to the system as input. And then the insects are each of them trying to solve that pattern, possibly by using some simplified evaluation function. You're going to easily determine in the end some worst match, that is, that insect which failed in evaluating this pattern very, very miserably, and that one insect which got a pretty good solution. Let's say here it has a known challenge-reply pair of this pattern leading to that reply. So you can say that that pretty well matches the input, and you are going to use the result of that insect. What I am thereupon doing, after this preliminary step of which one of you boys knows how to solve this the best, I am actually letting that insect evaluate the input and deliver the reply. I call this the best insect and the best match for that problem. Then this insect is going to compare the challenging pattern to its knowledge, and there it may use its actual evaluation function and find a reply. And then this reply will be output to the user. For the user, this will be not just the output by this insect, but that will be the result of having challenged the swarm. You understand, such a preliminary simplified evaluation function might still deliver you a somewhat different result than the actual challenge-reply pair used when you undertake more complex reasoning. That leads to the next concept, swarm evolution. I said you can make out here one insect which matched the problem particularly well and one insect which matched the problem particularly badly. How can we improve the swarm based on these ideas? And I say you can step by step update the swarm towards solving a problem. So to say, you do an improvement not just of a single insect, but you can use evolution to improve the entire swarm. And the principle is, the way the swarm solved a problem, it shall solve other problems in the future. In my implementations, swarm evolution works that way. You're having a challenge which is being presented to a swarm. The swarm has a best matching insect and a worst matching insect for that given problem. The worst matching insect is forgotten. It disappears from the swarm, it is deleted, it dies. The best matching insect is cloned, and then you have, so to say, 2 times the best matching insect. Then the clone is tasked with the solution of the problem and delivers the reply of the swarm to the outer world. This may actually change that clone. In any way, it at least exerts its influence. And then these insects, so to say, together with the clone, which may have evolved itself, constitute the new swarm. This is the evolved swarm, which has somewhat directed its set of insects to be somewhat closer to the actual problem presented to the system. As a matter of fact, as an extreme case of a swarm intelligence, my design of learning and handling world problems by means of challenge-reply pairs may be presented. And the swarm can thereby creep along topics by evolution and mutate more and more in one direction. You see here it starts this way, and each time a new problem comes, the swarm changes a little bit towards that problem. It creeps, so to say, forward into the direction of the problem space. that is going to be generally advantageous because mostly the problems which you are presenting to the swarm have something in common, otherwise you wouldn't be generally supplying them. And that way, the swarm can adjust gradually to your needs by forgetting those insects which are least useful and spawning forth those insects which are most useful. Now, let's look at the design of the challenge-response pairs. Even it can be seen as a very, very simple swarm intelligence, where each challenge-reply pair is a sort of insect, and each of them only determines whether the challenge presented to the system as a whole is most similar to its own known challenge pattern, and if it is, it shall deliver its response as output. But the evaluation of the patterns can be actually greatly parallelized, and each of them is of an identical structure but with different knowledge bases, and the same similarity function evaluates each of those knowledge bases versus the input in order to determine the best output. In particular, when you let such a challenge-response system learn, you can say, here is the system output, like what the system last replied to you. It may even have some longer pattern history or context. And then comes a human response. So you're creating a new challenge-response pair in order to learn this for future use. But that itself constitutes a step in swarm evolution. Now your system is forgetting something from its knowledge base which it didn't use for a long time or which was used a long time ago, and it replaces that with a new insect of a new challenge-reply pair which will then influence your system's behavior in the future. So a swarm intelligence can be even very quickly used in systems which operate by nothing else than challenge-response pairs. Some of you may have heard of so-called Blackboard systems, which were quite popular in the 1970s and 80s. The idea was that you have some problem and different parts of an artificial intelligence, each of which, looking at the problem, try to find a solution for it. I would like to make out here the difference between my proposal for a swarm intelligence and Blackboard systems. Well, first of all, the elements of the program looking at a given problem in Blackboard systems were fixed. You had different elements, and each of those elements was trying to match a part of the problem. Whereas in my swarm proposal, each of the insects is looking at the entire problem and trying to solve it. Moreover, each of those parts in the Blackboard systems were fixed. These were parts of the program. I, on the other hand, am proposing evolution of the swarm, so that the insects gradually approach the problem domain better and better. They are identical in their evaluation functions, while in Blackboard systems the different elements have their own and separate evaluation functions. Where my insects differ is only their local knowledge bases. My swarm design gives you nearly no limitations on the agents and the type of information handled. It may be visual, text, or anything what you wish. Moreover, the function by means of which information is evaluated is not determined either. You can use neural networks, statistical evaluation, vector comparisons, whatever you want. The idea is the swarm shall receive some input, it shall create some input, and it is necessary that it is able to evaluate how good some output is, so as to determine the best and the worst insect. And each insect can learn and develop by adjusting its own knowledge base. Optional is, as I mentioned, a cheap estimation function so as quickly to determine which insect shall be tasked with solving some certain problem. I'm saying optional because if you don't have such a function, you can use the actual evaluation function. Problem is, it will cost you more computing power, because you will then first solve a problem in earnest with all insects, and then, only then, will you select which one solved it the best. Now, what shall happen to with the reply? Well, you have generally two possibilities. And your swarm intelligence does not need to output it immediately to the user. It may immediately output it, but you have also the other option, implementing a sort of deeper reasoning, where the first reply is then presented again to the system as some sort of problem which it needs to re-evaluate. This is a design choice. You can have a system which operates on challenges and replies which it delivers immediately, but it can also be a system which is re-evaluating its replies itself several times so as to create more complex reasoning and to develop its knowledge bases further. This is really a design choice, and from this choice depends what you see as the behavior of the system. I would like now also to say a few words regarding individuality, and that's really the last topic. See, when somebody is talking about swarm intelligence, then people are immediately thinking like, yeah, but what is with the individuality? Like, who am I talking to when I am talking to a swarm of bees or something? Well, I say you are here giving into the illusion of conscience, and in fact, a swarm can very easily be regarded as an individual. You just have to get acquainted to the idea and used to it that a swarm is one entity, although it may consist of insects. And it is not necessary that an entity has conscience in order to be intelligent, as I have outlined before. In fact, look at this funny thing in our own society where you are having the situation of swarms consisting out of swarms, and so forth. It's a universal concept. You can say that a swarm of synapses is forming a neuron. You can also say that a swarm of neurons is forming a brain, and that's the only level which has developed consciousness by correlating patterns relating to it. A swarm of brains, so to say many people, has traditionally formed a society or perhaps a city. A swarm of cities creates a state. A swarm of states creates the international community. On each of these levels, from elementary electric impulses to complex social and political problems, and even the philosophical questions of the self, all of these issues are being solved by the respective swarm, which on some other level may be seen just as one insect in a larger swarm. I know that may be a little bit hard to grasp, but once you get used to this idea, and once you lose the fear of creating swarm intelligences, and once you learn to let them evolve, you can easily create quite powerful systems. I hope that was interesting to you, and I thank you very much for watching. I shall present to you examples of this approach in my future videos. I wish you a very pleasant day. Goodbye.